So we are going to discuss exercise 3.1, questions 25. Okay, so let me share my screen. Okay, I'm showing you exercise 3.1. So let me go and take out exercise 3.1. Okay, so exercise 3.1, questions 25. Okay, question 25. Question 25, find the derivative of the functions, blah, blah, blah. Okay, so I think that is kind of a straightforward questions. So questions 25, exercise 3.1. The question is gx equals to x minus 1. So we are going to use the formula x prime equals to x equals to limit z goes to x function fz minus fx z minus x, and then find what is the derivative for this formula. Okay, so question number 25 should be easy. So let me try to do this using my whiteboard. Okay. Okay, so exercise 3.1 questions 25. So the derivative by definitions at the point x is given by the limit where the function is evaluated at a point z minus the value at point x divided by the gap between z and x, and then you let the values of z to goes to very close to x. So this is equivalent to the other way of writing. So you can write this as, I think, f of x plus h minus f of x divided by h, and then you let h goes to 0. So these two are equivalent form of writing the derivative. But anyway, we are not going to use the second expression in terms of x. We are going to use it in terms of z. Okay, so it should be exactly the same thing. Okay, so now you just have to write down the expressions for fx given by the functions. Here, function in terms of g, but whether it's g or whether it's f is still referring to the same thing. So instead of writing gx equals to x over x minus 1, I'm going to use the symbol f to represent the function x over x minus 1. So it doesn't really matter, right, whether this is written as g, whether this is written as in terms of g, or in terms of x, right? So it's just a symbol. So try not to be confused by the symbol of that represent the function. Whether you call it a function of a name g of x or f of x, it's still the same. Okay. So then you just write down the expressions. Okay. So f is just f. So x minus 1. Then you just try to write out what is f prime, which is equals to the limit of z goes to x for the function f at z. Yeah, so let's see how was the question. I think the question, I have to look back at the question again. So the questions is find the derivative of the formula z. Yeah, so how are you going to write that in the derivative of the function of z? Alternative formula for derivative, find the derivative of the functions gx equals to x minus x. So now my fx, so if I were to follow this exactly, then it will be quite confusing. Okay? So that would be z minus 1 minus x over x minus 1 divided by z minus x. So I have to think of a way to make these simplifications. So I think that simplification would not be as easy, but let me try to use my own way. So I'm not sure what is the correct answer, but I'll use my own way to solve these questions. Okay, so my way is just the same thing. I think this expression seems to be not very well. Let me try to think of my own. My way is that I'll define h to be just equal to z minus h. So here z is considered as a variable. Okay, so let me explain again. When you look at these expressions of f prime x, here x is supposed to be fixed, right? X is supposed to be fixed, and z is supposed to be varying. Okay, so z is a variable that is changing, whereas x is fixed because you're going to evaluate the derivative of the function at a fixed x. That is what it means by f prime x. F prime x means you fix the values of x and then you let z to tend towards x. Therefore, x has to be fixed. So you fix the values of x, and then you change the values of z. But z being a variable, you can sort of like invent a new variable to replace z. So instead of working with z, I'll try to translate, or well, I will try to sort of like translate z into another variable, h. So instead of changing z, I change h, and I call h to be equals to z minus x. So that is how I would do my calculations. I'm not going to work in terms of z, I'm going to work in terms of h. So if you look at this equation, h equals to z minus x, what you can see is that you have only one variable. What is a variable? It is actually z. But since h is defined as the variable z minus h, then you can think of, instead of working with z, you work with h. So just let h to change. Right? So either you change z or you change h, because they are all equivalent to each other, which is tied to this equation. When I say tied, I mean the variable h is tied, T-I-E-D, tied to z, right? So sometimes this happens very often in physics. Instead of working with a variable z, you work with a variable called h, right? So by doing that, your expression could be somehow simplified a little bit. So it is very often to change the variable by making such a transformation. We call it transformation, right? So this is a transformation I'm going to make. I'm going to make the work in terms of, instead of in terms of z, I work in terms of h. So by redefining my z, then I'll be able to rewrite this as a limit of, since the h is defined at this, right? So it infers that if z is getting close to h, to z, it just simply means that h is shrinking to 0. So I'm just translating again the derivative into the form of variable h, which is nothing much different than the previous definitions, which is z is h plus x, right? So this is my z, then so I can continue to write on. This is z minus h. So again, z is h plus this one minus 1, then minus x over x plus 1 divided by h. Okay, so that is my trick. So I'm not actually working in terms of z, but I'm working in terms of h. So that is my answer. So I would say that the limit of the function z goes to x, this is dot dot dot, is the same as the limit of h goes to 0, dot dot dot, dot dot dot, is the same as this expressions. So I'm going to simplify these expressions, then string h to 0. I think this has been done in the exercise. So you just have to work out the algebra. it should be like x plus h times x minus 1 minus x times x plus h minus 1 divided by h times x plus h minus 1 x plus 1. Okay, so you have to do these algebraic operations. You have to carry out these calculations. Then you see what is the result of this expression. So maybe if I want to do this, let me try to do this using Mathematica. X plus, sorry, the expression is x plus x, sorry, x over x minus 1. Okay, so that is my expression. Okay, so I'm going to simplify this expression using Mathematica. So I go back to my Mathematica. Okay, here. Okay, so I'm going to have my x. So the expression is to simplify it using x over x minus 1, right? So here I'm going to take the difference between two terms, which is the first term, and then this is the first term, this is the second term. So the first term, the whole thing divided by h. So here, instead of x, I have x plus h. Here, instead of x, I have x plus h. So that is this expression that I want to simplify using Mathematica. So this is, yeah, so let me try to see if I can simplify this using Mathematica, which allows me to get answer simplify. Yeah, so that is my expressions. So I have simplified this to be just 1 over minus 1 plus x, and then minus 1 plus h plus x. So by doing that, I am able to simplify the expression into this form. So then when this is taken to the limit of h goes to 0, so what left is just set the h goes to 0, right? Because the limit here is the same, so it is x squared. It's x minus 1, x minus 1. So the answer is still the same. It will become just a square here. Right. So the answer is that in the limit when h goes to 0, then you get minus 1 over x minus 1 squared. So that's the answer for the simplification. I think that exactly is the same way how you would do it using the h notation. So the tutorial questions ask you to prove this using the Z, but I don't really answer the question directly. I just translate the Z into that.
Doctor, I found using Z.
You found what? You have a solution for that?
For Z you can do also.
Okay, fine. So you want to share your screen with me?
Oh, it's not on my screen. Wait.
Okay, so it will be good if you can share the screen. Let me walk out,
Wait.
stop sharing. Then I'll wait for you to share your screen. I don't really have that solution for these questions, for this answer. Okay, thank you very much for you to share.
Wait, I open OneNote lah.
Now my okay, so are you
Yeah,
sharing your
got it.
recording? Yeah, sure. Please do. Yeah.
So it was like okay, ZX. Sorry, wait,
Oh,
my paper
we have a
my
lot of
paper
time,
very
so it's okay.
messy. Without wait, yeah, over wait,
You have to highlight the whole thing. Yeah.
I like the whole thing. Wait, what like that one?
Yeah, I think you should. Yeah, it's right.
It's fine lah, it's fine.
Yeah.
Like
Slash.
over Z minus 1 times z minus 1 times x minus
X
1.
minus, yeah.
So it's like that, right? And then
Yeah.
wait, and then equal to the you'll find if you do this, if you times in, you'll find yeah, zx minus z minus zx plus x over z minus 1
X plus 1.
x minus 1, yeah.
Yeah.
So in the end you get like you get this. Wait, this one no problem already. I just ignore this. So you get minus z plus x. And then if you get this one and then you divide the whole thing by the z minus 1, right? So
Yeah.
you get negative the whole thing by z minus 1, because this one is actually just this up here is actually just
Yeah. So
negative
cancel off.
z minus x, right? So this one you divide by z minus x.
Yeah, you cancel off.
You
Yeah.
cancel off, and then you get negative 1, and then you get negative 1, and then x, this z is also x, is limit x, right? So it's x
Yeah.
minus 1 square, and then negative 1 x minus 1 square. The same answer.
Okay. So I think you got it. So you just have to carry out the algebra. That's what you are saying, right?
Yeah, they basically combine the two fraction.
Okay, fine. So that is a good suggestion. So maybe you could do that. Okay, so thanks for your sharing. Let's go to the next questions. So I'm going to look at another questions, which is on questions 3.6, exercise 3.6, exercise 3.6, questions 65, exercise 3.6. Question 65. Okay, so this is good. This is not a formal session. It's just a recording. So we have a lot of time to discuss this. Questions, exercise 3.6, question 65. So we have question 65 here, which is implicit differentiation parameter. Assuming equations define x and y implicitly as differentiable functions, x equals to this and that. Find the slope of the curve at the point of x t equals to blah blah blah. So this is a question of 65. So let me copy it down. X plus 2x 2 equals to what? To t squared plus t. So let me see if I understand this correctly. Then you have y square root of t plus square root plus 2t square root of y equals to 4. And you're supposed to do this at t equals to 0. So assuming equations define x and y implicitly as differentiable functions, then find the slope of the curve at x equals to ft, y equals to xt, given the values of t. So we are looking at this kind of very complicated expressions. See if I can highlight this. Okay, so we have this expression and this expression, and our job is to find out what is dy dx, okay, at t equals to 4. So so our job is to find what is dy dx as a function of t. So in order to do that, let's see how I do this. Okay, so I have not actually done this kind of question before, but I think it would not be difficult. So I'll give it a try. Okay, so this is my whiteboard. Okay, so let me copy down the answer, the questions. So I have the first question, x equals 2x 2/3 equals to t squared plus t. So when you do that, when you expect that from here, you'll be able to obtain dx dt. So when you obtain dx dt from this equation, it will be some expressions, I think, in terms of t. That is what I expect. Okay, that will be some kind of function in terms of t. And then for the y equation as well, you'll be able to get dy dt. I think that is what we want. We have to find out what is dx dt and what is the g dy dt. Okay, so once we have the expressions for y of f and g, then dx dt, so and dy dx for the functions will be then clear. So you get dy dt, then dy dx could then be just obtained as y prime y dot divided by x dot, which is a functions of t, right? So this would be the f over g. Okay, so then you'll be able to evaluate the slope of the function at any point of t, right? So I think that should not be difficult. So the first point here will give you dx dt, right? So dx dt will give you this will be 3x half. Okay, then you have dx dt. I think that is what you get. Now let me know if I'm doing it incorrectly. So this would be 2t plus 1. Okay, so I have my dx dt. Okay, dx dt would be then equals to 2t plus 1 divided by 1 plus 3 square root of x. So that is my first part of dx dt. So I'm going to, now I think in that case, my expectation is not quite true, because the functions of dx dt is actually not a simple function of t only, but involve also a square root of x. But anyway, it would not affect my argument, because I'll be able to tell what is the values of x from the values of t. So anyway, I'll carry out these calculations to work out what dy dt is. So let me clean the space for dy for the dy dt. So clean up, do it fast. Okay, so I have to clean up this point for the y function. Okay, the parameter equation for y is y square root t of 1, which is a square root. I write it as like this, plus 2t y square root equals to 4. So I'll keep this later on. Maybe I should write this down because I need it later. 2t plus 1 plus 3 square root of x. So here I would then write down the formula for my dx. So I wrap up this one because I already copied it down on my paper. I'm going to reproduce it later in a minute. I need a space. Okay. So let me carry out the derivative here. So the derivative here would be the derivative of y dy dt multiplied with t plus 1 with a square root, plus y times the derivative of square root of t plus 1. So this would be multiplied with half of t plus 1 minus half. Okay, so I'm applying the chain rule to write down this expression. So this first term is for this term plus this term is for the derivative of this. Okay, then I'm going to write down the expressions for the other term, which is this one. Okay, so I'm going to add 2t and then take the derivative of y square, y of square root. So derivative of this would be then half of y minus half. Okay, so that is this part. Then I have to also multiply with a factor of dy dt. Okay, so the factor of dy dt, maybe I just top off this one, and then just cancel off the factor of 2. Okay, so that will give me the derivative, the first derivative of this. Then I have another derivative, which is 2 times y of square root, and then d dt of t. Okay, then here right hand side is just 0. So I have kind of complicated expressions for my dy dt. So I'm going to collect my dy dt. So this will be square root of t plus 1. Well, then I have another factor here, which is plus t times square root of y. That is what I will get. And then I get equals to, I throw the rest to the other side. I have minus 2 square root of y. And then I have another factor of minus 1 over, which is y 2. Then I have a square root of t plus 1. Now let me know if I am wrong on that. So that seems to be kind of complicated. So let me copy it down. My dy dt is equals to minus 2 square root of y minus y over 2 of square root of t plus 1 divided by t over square root of y. Wow, it's complicated. T plus 1. Okay, so now I have the expressions of dy dt and also have the previous expression for dx dt. So dy dt is a function of t and y. Dx dt is also a function of t and y. So I have copied down the dy dt and dx dt. So now let me try to do this. So dy dt, which I have derived earlier on, is a complicated function that is expressed in terms of, so let me call this dy dt as a function of g. Okay, just call it g instead of y. It's a function of g in terms of t as well as y. So if you want this to be written down explicitly, it's kind of complicated. It's minus 2 square root of y minus y over 2 square root of t plus 1 divided by t over square root of y plus square root of t plus 1. I might make some stupid mistake, but you can repeat my calculations just to be sure, okay? And then you just correct my calculation. Then dx dt is a complicated function in terms of, say, I call it f, in terms of t and x. And according to my record here, this is equals to 2t plus 1 divided by 1 plus square root of 3, sorry, square root of 3x. Okay, so we have this complicated function of f and g. Then dx dt is, sorry, dy dt, not dx dt. dy dx is then equals to the derivative of g in terms of t and y divided by the function of t and x. T and x. Okay, so that is the expressions which I have arrived at like this. Okay, so what the question was asking is that question was asking the question was asking at t equals to 0. Right? At t equals to 0, what is the slope of the curve? So this is a complicated function in terms of x and t. So what I have to do is that I have to calculate the values of g when t equals to 0. When t equals to 0, I have to figure out what is the values of y. Okay, so how do you know the values of y? So the question now translates into that in order to get the answer, I just have to substitute in the values of t equals to 0 and the corresponding values of y when t equals to 0. So that gives me a number for y. I don't know what is this, but it should be a number. Then I have to then also have to be able to throw in the values of x when t equals to 0. And the values of t at 0, I call it x naught here. So in order to calculate the values of the slope for this parametric curve when t equals to 0, it requires me to know what is the values of y naught and x naught. Once you know what is the value of x naught and y naught, then you substitute the values of y0 and x0 into this expression here. Then downstairs will become t equals to 0. Then you'll be able to get the functions of g at 0, y0, and also with the values of x0, you'll be able to calculate the values of the function at the function of t at t equals to 0 and x equals to x0. So you now translate into this expression what is x0 and what is y0. So the x0 and y0 answer could then be obtained from the parametric equation itself. So I have to go back to the parametric equation. The parametric equation says you have this expression of x plus 2x3 over 2 equals to t squared plus t. So it is actually quite straightforward, right? So when t equals to 0, x equals to x0. So x0, so it's really easy understood that the x0 is just equals to x0 1 plus 2 x0 half. I think that is the answer, where the t is just equals to 0. Right? When t equals to 0, then these equations reduce to this. Okay, so then what is the x0? x0 is just x0 equals to 0, and then I think that's the answer. So this is always positive, right? So it's not possible for the factor here to become 0 because square root is always positive in the value, right? So the answer is that when t equals to 0, x0 is equals to 0. So that is what I got, x0 equals to 0. And then I go back to the equation that define my y. So the y is equals to t plus 1 plus 2t square root of y equals to 4. So when t equals to 0, I have my values of y equals to y0. So this equation then reduced to y0 square root of 1 plus 0 equals to 4. So it just simply says y0 equals to 4. So I have now got my answer. X0 equals to 0, y0 equals to 4 when t is equals to 0. So then I just have to call out my expression for the dy dx. dy dx is equals to y prime over x I dot y dot, and then I call this y dot as previously expressed as very complicated functions. Maybe I write it down. Okay, so y dot is a function. I call this what I call this g, right? So I call this g. The g is minus 2 square root of y minus y over blah 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 2t plus 1 divided by t over square root of y plus square root of t plus 1. So at t equals to 0, y is equals to y0 equals to 4. So then this expression can be easily simplified by substituting the values of y with 4. Then this will be substitute as 4. Then substitute t as 0. So when t is equal to 0, then this become just 1. So then this whole thing will be just simplified to be just equals to 1. Right? So then this factor will be just equals to 2. Okay, like this. So you can do this for the rest of the t. So when t equals to 0, this term will just give you 0. And then this term will give you 1. So this term just give you 1. So finally, you have expressions for y dot when t equals to 0 as this number. Now this is just the algebraic equation that I was doing in a rush. Right? I might be wrong, but I think the correct answer doesn't really matter. That is what I think. So so this is expressions for the abscess when t equals to 0. When t equals to 0, abscess of y dot is just g at t equals to 0 at just minus 2. 2 times 2, 4, 4 minus 6. So this would be minus 6. Okay, so that would be expressions of minus 6 for the y dot. And then how about for the x dot? So for the x dot, you write down the expressions. These are all algebra. Since I already do it, maybe I just finish doing this. So x dot as a function of t, and x is just what I call f of t, which I have copied down earlier on. It is just 2t plus 1 or 1 plus 3 square root of x. So I have already shown you that at t equals to 0, x naught is equals to what? Is equals to 0. Yeah. So it is quite easily shown that f at t equals to 0, which is x naught at t equals to 0. I got x naught. So the answer is just equals to 0, 1. So 1 over 1, it's just equals to 1. Right? So just substitute t equals to 0, x is equals to x equals to 1, then you got 0. Sorry, x is 0, then the whole thing is 0, then upside is 1, downside is 1. So that is 1. So the answer is minus 6. Now I'm not sure whether my calculation is correct on the screen, but I suppose this is how you do it, right? So you just make use of the algebraic equation, find out the values of x when t is 0, find out the values of y when t is equal to 0. Then you use the formula dy dx equals to dy dt over dx dt. And how do you get the values of dy dt and dx dt? You get the values of dy dt and dx dt by using that. Let me see if I can show you. This is 3.6. So you can easily obtain the, let's see, I can make it larger. Yeah, you can make use of the equations here. Make use of the equations here to allow you to get what is the x dt, and use this equation to give you y dy dt. Right? So you get a very complicated functions. Then you just substitute in the values of t at 0, x at x naught, y at y naught. Then dy dx at t equals to 0 will be then just x dot at 0 when t is 0 divided by t at 0, and now just carry out the algebra. So it's a very lengthy algebra, but basically it is a way how you do it. Now again, if I make some mistakes during my calculation and it didn't come out to be correct, then it is not very important at this point. The important thing is that you know how to carry out this for yourself. Okay, so that. Okay, so we are going to continue discussing a new questions. Exercise 3.4, questions 43. The limit of the tangent of 1 minus sine t over t when t goes to 0. So this is the questions that we are currently trying to answer. So in order to answer these questions, you have to understand two important concepts which is discussed in topic 2.6 about the idea of continuity and theorem 10. So you have to understand the continuity and limit before you can apply it to theorem 10. So it's just a revisions which I'm going to repeat it here. So let me go back to the my iPad so that I can write and discuss it here. So first of all is about the idea of continuity. Continuity means if you have a function f which is continuous, then it means that the function that is continuous at x0, then the limit of the function at x0 must exist, and it must be equals to the values evaluated at the function of evaluate at the function f at x0. So this, if left hand side equals to the right hand side, then we say the function is continuous. So in other words, if a function is continuous, then its limit exists, and the limit is just equals to the values of the function evaluated at x0. So if you refer back to the theorem 10, it says this. It says It says if you have a composite functions made of f g composed of f, then if the function of f is continuous at c and g is continuous at f of c, then the composite function of g composed of f is also continuous. So if you have two functions g and f, where f is continuous at c, g is continuous at f of c, then the composite function of g composed of f is continuous. That means that the limit of the composite function g composed of f exists, and the values of the limit for g composed of f just equals to the values of the composite function evaluated at c. So specifically, it means this. The statements, if you were to look at the way how I write it, is like this. If you have a composite function, say g, which is continuous at c, and then you put these values of the g into f, and then you take the x goes to c. So here let me call c equals to x naught, so that it is referring to the same limit of x naught instead of using c. Then it would mean that this is just equals to the values of the composite function evaluated at x naught. Okay, so if the limit of the composite functions exists, then that limit must be equals to the values of the composite function evaluated at x naught. So you make use of this idea and theorem 10 to answer the questions we was talking about. So the questions we are talking about is this, right? It is this. We want to show that the sine limit of tangent of 1 minus sine t over t is equals to some number. Okay, so let us try to answer it here. So once I have explained the concept of continuity and theorem 10, then we can start to answer these questions. So let me go back to my whiteboard. Okay, so the whiteboard here says I have a limit for x goes to 0. So here is not x, this is called t. The question says is t. Then you have a tangent of 1 minus sine t over t. Okay, so I'll call my ut to be just 1 over sine t. This is actually what I always called as the what I call the interior functions. Then I have another function f of u. I call the external function tangent u. Okay, so what I want to show is that the limit of the function u t, when t goes to 0, it exists. Okay, it exists and its value is just equals to something, right? So you can prove quite easily that the limit of this function exists and it's just equals to the limit of 1 minus sine t over t, and when t goes to 0. So the limit of sine t over t when t goes to 0 is already known. We explained that and we've proven that using some geometrical argument. Remember, we draw the circle and then there's a triangle inside the circle, then we take the limit, then the geometrical construct allows us to find out the limit of sine t over t, and turns out to be 1. So you have a limit of 1 minus another 1, so this actually gives you a values of 0. So what I am saying here is that the limit of u at t equal to 0 exists and its value is just 0. So that established the first steps, that the u is existent, or the u exists when t tends to 0. So the limit of u exists. Now we have to prove another thing about the limit of the function when u tends to the limit of u tending, let me say it again. So we are now going to explain the limit of the function u. Right, so in the limit t tends to 0, u tends to 0. So in that limit, we are then trying to ask the questions of whether the function fu has any limit when u tends to 0. So in the limit when u tends to 0, let me write it down somewhere. Okay, let me write it down. Upstairs, I need some space. So we answer the questions. What is the limit of the function fu when u tends to the limit of 0? The 0 here refers to the limit of u when u tends to 0, which is 0. So this is the limit of tangent u, right? So the limit of tangent u when u tends to 0 exists or not? Answer is yes. It is quite straightforward to tell that tangent has a limit when u goes to 0. The reason is very simple. Basic trigonometric functions such as cos, sine, and tangent, they are continuous and their limit always exists. Like continuous trigonometric function is known to have that kind of property. We have actually mentioned that also explicitly in the lecture notes. Tangent u is continuous at when u tends to any value within its domain. Yeah, I think that is a correct statement. Especially when u tends to 0, then tangent u just tends to 0. So the limit of tangent u exists as well. So at this stage, we have established the very simple fact that if you have a function called tangent of 1 minus sine t over t, which you write it as f composed of u, and this whole thing is a function of t, then we have just proven that the limit of u, the limit of u, t, when t tends to 0 exists and is equals to 0. Then we also have proven that the limit of fu, u tends to 0, also exists and is equals to 0. So we have proven that the composite functions, in this composite function, the limit of u exists and the limit of f at u also exists. Therefore, according to theorem number 10, then you have automatically proven that this function, which is the composite function made of f composed of u, also exists, and its value is just equals to 0. Okay, so then we come to the conclusion that the limit of t goes to 0 of this is just equals to 0, because the limit of u is 0, the limit of f at u equals to 0 is also 0. So that is the answer for these particular questions. Okay, so that finish up questions 43 in exercise 3.4.